Hello class, this is CSE 4600, section 62, chapter 1, part 2, fall 2024. I hope all of you are doing alright on account of the fires and the storms happening right now in the San Bernardino Highland area. Because, you might be affected directly by the fire, or you might just be breathing in ashes, but still, I just hope you're doing okay right now, because it's not good happening right now. It's not good what's happening right now. So, but at the same time, hoping that hoping that it gets resolved soon enough. For now, we're going to continue our discussion on chapter 1. So, right where we had left off previously, we were looking into what we were about to look into what our system calls. So operating systems have two main functions: provide abstractions to programs and managing a computer's resources. So the resource management aspect of an operating system, that is done automatically, so the user never sees it. The interface between user programs and the operating systems, it's primarily about dealing with abstractions. So remember what I said about having a programmer operate a hard drive by spinning the platters and moving the read-write head? Yeah, no programmer is ever going to want to do that, because if a programmer writes code that would do that, they have to do the same thing for some other model of a hard drive. And what if the user replaces their hard drive with a different model? Suddenly your code no longer works and you can't read anything anymore. So that's why we have these system calls for example, reading from and writing to a file. Because the idea is this: even if the user upgrades their hard drive, you don't have to rewrite the programs every time the user changes hard drives. You don't need a whole new program for every hard drive model out there. Also, solid state drives are a thing. So, with a solid state drive, there are no moving parts to be had, so we don't have a read-write head to move. We don't have platters to spin. If a program was based on those operations and you had an SSD, the program wouldn't work. So that's why we have, for example, read and write operations that are agnostic of the hardware itself and would work regardless of whether it's a hard drive or a solid state drive. This also makes it easier to write programs for, because again, would you want to write a program that moves the read-write head and spins the disks? It would be vague to simply just say operating systems have system calls for reading files. So we're going to look at the example provided by POSIX. So before we begin, keep this in mind. A single CPU computer can only execute one instruction at a time. So if a program needs a system service, it needs to execute a trap function to transfer control to the operating system. The operating system then determines what the calling process wants by inspecting the parameters, and then it carries out the system call, and then after that it returns control to the instruction following the system call. So when you call a function in a program, what happens is your program's gonna need to jump from where it was to some new area in the memory space, and then when it's done, it has to jump back to where it was, but +1, so it's reading the very next instruction after that. A system call is like that, except we're also handing control over to the operating system. So let's look at that read system call. So there are three parameters for this: FD, buffer, and bytes. FD, that's a file descriptor. That's a file descriptor. It specifies the file. We'll talk about how we get FD in a little bit too. The second parameter, that is buffer. That's a pointer to a buffer. And the third byte, n bytes, that's the number of bytes we're gonna try to read from a file specified by FD. So we could have a C program that has this line of code, though technically it would be converted into machine code, but for ease of understanding, it's gonna execute this line of code as it is, with the high level terms and all. So, read is going to return some value, and that value is the number of bytes that was actually read when you tried to read the file. So this count here is going to have the number, it's going to store the number of bytes that we tried to that we successfully read from the file. So, for example, we could try to read 1000 bytes from a file, but it could have only 800 bytes because, well, we could let me back up. For example, we can try to read 1000 bytes from a file and only get 800 bytes read because, well, that's how big the file was, and we hit an end of file while reading. If we can't read the file, say there's a disk error, or we passed in something wrong, or we tried to read a file that doesn't exist, or we tried to read a file that we don't have permission to read, then that number of bytes read, that's going to be -1. So read's going to return -1, and the error number, so we know what went wrong specifically, that error number is going to be put into some global variable called errno. So here's an 11-step process for how this read operation works. The first 3 steps have us push those 3 parameters onto the stack. So that's going to be n bytes, the address of the buffer, and FD. Though it's pushed in reverse order. That's just a legacy of how POSIX systems work. Step 4, after we had pushed those 3 parameters, we're gonna call the read function. When that happens, we're gonna jump to some other part of the user space, and we're gonna do step 5. We're going to put the code for read into a register. And then, after that, we're going to our next instruction, and that is the trap instruction. We're gonna trap to the kernel, and when we do that, we're handing over control to the operating system. When we trap into the kernel, we're gonna go from the user space to the kernel space. So we're going to now dispatch the kernel code that starts following the trap, examines the system call number, and then it dispatches the correct system call handler. Okay, so this is going to be a table of pointers, the system call handlers indexed by system call numbers. So the read instruction is going to have some number associated with it. We're going to look up that number in this lookup table here, and then it's going to have a pointer to some system call handler. That handler runs, and then after that, we're going to be able to read our file. Once we're done, we're going to return here. Once it's done its work, control may be returned to the user space library procedure at the instruction following the trap instruction. And then we're simply going to return as we normally would. So when we call a function, it's going to be added to the stack to keep track of where we are in the program. We're going to do that thing, and then we're going to return from that function, and then we're going to pop that function from the stack. So step 11. We clean up the stack, and that's usually done by incrementing the stack pointer. So, okay, so that's an 11-step process. So we push our 3 parameters onto the stack, we call read, we put that read code into the register, and then we trap into the kernel. The dispatcher looks for the appropriate system call handler, that system call handler runs. When we're done, we return here, and then we return to the caller, and then we increment SP. That's our stack pointer, by the way. So that's an 11-step process of how read works in a POSIX system. So there's a little bit of a hiccup that can happen, and it's this. What happens if the program is trying to read from the keyboard and nothing's been typed in yet? At that point, if you just look at it as this, then the computer is going to be doing nothing because the computer is going to be waiting for input. So, remember what I said about keep the computer busy? Keep the CPU busy? The operating system's just gonna try to run something else. At that point, the caller is blocked, and the OS will look for some other process to run. And once the desired input is available, the process will get the attention of the operating system, and then we're just gonna run steps 9 and 10 again. Right? So now we're gonna look at a few. We're gonna look at some of those heavily used POSIX system calls, and one of them is called the fork. So fork is a good place to start. So if a process calls fork, it creates a copy of that process. Calling fork creates a new process that's a duplicate of the original. The duplicate is what we call a child process, and the original is the parent. Both processes have the same code, but they are copies of one another. Let me see that again. Fork makes a copy of itself, but they're two unique copies. Here's the other thing. Processes have process IDs, so if one process is labeled 1, its child process could, for example, be labeled 4. And yes, I'm using my trains to demonstrate this because it's the first thing I had that were copies of one another. When we call fork, it has a return value, and that's going to be the process ID of the child process that was created. For the child, that return value is going to be 0. But for the parent, that return value is the process ID of the child. That way, the calling process, the parent process, will be able to keep track of its child. And why would that be useful? Well, you'll see. We're gonna look into the operation of what's called a shell program. In most cases, after a fork, the child will need to execute code that is different. So in most cases, after a fork, the child will need to execute code that is different from the parent, such as with a shell. So this is the shell program I'm talking about. So what is a shell? Well, it's a program. It reads commands from the terminal, and when it reads that command, it's going to fork off a child process, and the child process executes that command. And when that child process is done executing, well, while the child process is executing, the parent process is just basically waiting for its child to finish executing. And when it's done, the parent process is now free to read another command. Let me adjust my lights. Here we go. So the shell, the parent, waits for the child to finish executing by calling the wait PID system call. So for wait PID, we pass in a value for PID which specifies the child that we want to wait for. Or we can wait for any child if we pass in -1. When wait PID completes, the address pointed to by the second parameter, statlock, will be set to the child process's exit status. So here's wait PID. It has 3 parameters. PID is the process ID of the child process. And remember, wait PID, that's being called by the parent. So the parent forks, and then it waits for its child to finish its job. The child process is gonna execute and then hopefully finish. So maybe it would help to look at some code. So here's some code for a stripped down shell from the book. So consider how fork is used in this following code here. When a command is typed, the shell forks off a new process. So we're gonna type prompt, display prompt on the screen. We're gonna read a command from user input, and then we're gonna fork. If fork does not equal 0, then if we're the parent, we're going to call wait PID. Basically, we're waiting for the child to exit. Otherwise, if you are the child, you're gonna call some other system call, and that is exec VE. What is this? The child executes the user command. The child executes the user command by using the exec VE system call. That causes the child's entire core image to be replaced by the file named in the first parameter of this exec VE system call. So command here, that's going to be your command that was typed in by the user. Technically the system call is exec, but several library procedures call it with different names and with different parameters. In the most general case, exec VE has 3 parameters: the name of the file to be executed, a pointer to an array of arguments, and a pointer to something called the environment array. So let's imagine we type in a command into our shell. That command is cp file1 file2. So this is going to copy the contents of file 1 to file 2. So we type that into our shell. The shell is going to fork. The child process is then going to replace its memory contents with the code from the file cp. Because this cp here, that is actually a program. So really what's happening is the shell program, forks a child. The child then finds the program, replaces its code with the code of the program, and then it executes this program called cp. The main program of cp, like that of most of its other C programs, contains this declaration shown below and has 3 parameters. So you may have written C programs or C++ programs and have encountered stuff like this: argc, argv. What is this? Well, argc, that's the number of items on the command line, and that includes the program name. Argv, that's a pointer to an array, where the ith element of that array is a pointer to the ith string on the command line. And envp, that's just used to customize how the user wants to perform certain tasks. When the command cp file1 file2 is entered, the child process is gonna run. Okay. So when we type in this command into the shell, it's gonna run the program called cp. Well, technically, it's the child process that's gonna end up running it. When it does, it's gonna have these following command line arguments passed in. So argc, that's gonna be 3 because, well, there are 3 arguments being passed in. Even though it looks like 2 arguments in the form of file 1 and file 2, we count cp as an argument as well. Argv, that's a pointer to an array where argv0 is cp, argv1 is file 1, argv2 is file 2. We don't really work with envp in this case, so the third param of exec VE, that's 0. Let me go back up to a few slides. Look at exec VE. We're not really working with environment. Yeah, we're not looking at this. We're not looking at environment here, so that's going to be a 0. So no envp here. So that's how a shell program works, and I might want to assign you I might assign you a assignment where I might give you an assignment where you try to write a shell program for yourself, but maybe in a little bit. We'll see. It turns out that exec is the most complex of all the POSIX system calls, so other system calls you'll see, they're gonna be much easier to understand. So what we just looked here is, some of the hardest system calls to understand. So everything else at this point is gonna be, well, easier. Consider the exit system call. That is called when processes are finished executing. And it has one parameter, and that's the exit status. That's gonna be some value from 0 to 255, and it's returned to the parent via stat lock when in the wait PID system call. Processes in Unix have their memory divided into 3 segments. Text, that's the executable code. Data, that is global variables. And stack, that's just temporary data used when invoking functions. This goes downwards from the maximum memory address. Other sources might have a 4th segment called the heap. This is for dynamic memory allocation, and it would start at the end of the data segment, and that part grows up. And one of the tasks that an operating system also has is to make sure that the stack and the heap don't crash into one another. Between the stack and the data segments is a gap of unused space. So expansion of the stack segment is done automatically. However, expansion of the data segment requires its own system call, BRK, which specifies the new address of where the data segment ends. Also, the BRK system call is not defined by POSIX, since programmers are encouraged to use the malloc library procedure for dynamic memory allocation. And this is because the subject of standardizing it wasn't thought to be suitable, since few programmers use it directly. Okay, so these were all system calls for process management. And to recap, let's go back to our table. PID creates PID equals fork. Fork makes a new process that's initially a copy of the calling process. Wait PID has the parent process wait for its child process to finish executing. Exec VE replaces a process's core image with a new program. And exit, basically terminate process execution and return status. So those are the 4 main system calls related to process management. Now we're going to look into file management, which is this entire table here. And that is section 1.6.2. We're going to be looking at a few system calls related to that they operate on individual files. So before you do anything with a file in a program, before you do anything with it, you got to open it first. So we have a system call for opening a file. Pretty simple. So you open a file, you have to specify what the file is. Also, you got to specify how you're going to open it. Are you going to open it in read-only mode or write-only mode, or are you going to do both operations? Are you going to do reading and writing? The open system call returns a file descriptor, and we're going to use that for our read and write operations. So when we call read, and this also applies to write as well, we pass in that file descriptor so we can read data from a file and then put that into a buffer. That's in the case of read. If we're writing to a file, we're going to pass in that file descriptor, and then we're going to write data from a buffer into a file. So we open our file and we get a file descriptor, and then we use that as, and then we pass in that file descriptor for when we want to read from a file or write to a file. So once we're done reading or writing a file, we gotta close it. So there's another system call for that. So we pass in the same file descriptor as we had before. So open a file, we get a file descriptor, we can do stuff with it, we can read, we can write. And when we're done, we have to close it, we have to specify what file to close. Here's another thing. Programs typically write files, typically programs write the files sequentially, but some files require random access. So we might want to read from the end of, we might want to read or write from starting at the end of the file, or we might want to go to some arbitrary location in the file. That's called random access. So we need to change the position. Okay, so associated with each file, there's a pointer that indicates the current position in that file. So we want to change that value so it points to wherever we want in the file. Normally, this would point to the next byte to be read or written to, but lseek, that's another system call, changes the value of that pointer, so subsequent reads and writes can be anywhere in the file. So, lseek, this is a system call. We pass in our file descriptor, but we also pass in two more parameters as well. Of course, fd is the file descriptor, as I mentioned. Offset, that's the position in the file, and whence, that tells whether the file position is relative to the beginning, the current position, or the end. The value returned by lseek is the absolute position in the file in bytes after changing the pointer. For each file, Unix keeps track of the file mode. So, regular file, special file, directory, whatever. It also keeps track of the size, the time of the last modification, and other information. So, stat can be used to get this information. So, if you want to use this one, we pass in the name, and that's the file name, and then we pass in the address of a buffer. So we're getting stats on a file. But if we want to get stats on an open file, we have fstat. So we get a file's status information or an opened file's status information. So that was everything for file management. Let's look at directory management. So much like with files, we can make files, we can also make directories. So we have system calls for making directories. We also have a system call for removing directory. Yes, so make directory, we pass in a name and a mode. Remove directory, we just pass in the name of the directory. So we can create directories, we can also remove directories. We can also link directories. Link is to allow for, the system call link is to allow, it's to allow the same file to appear under more than one name and often in different directories. So imagine you have a file shared between two users and they want to be able to access the same file in a convenient way. And it's not the same as giving each user a copy of their own file. Here, we want it so that any changes made by one user is made immediately available to all other users. So link will do that. It will allow the same file to appear under more than one name, and unlink removes that link. So consider two users, AST and Jim, who have their own directories. AST executes a program that contains this system call, and after that, AST has an entry called note here, which refers to the file called memo that's in Jim's directory. So what happens here? So what does Link do behind the scenes? Well, it's simple. He's crucifying Korax. No, that's kidding. So what happens is this. Every Unix file has a unique I number, and that's an identification number. That number is an index in a table of inodes, one per file, telling who owns a file. A directory is simply a file that contains I numbers, and for each I number, there is a ASCII name. So in AST's directory, we have in AST's directory we have 4 files. They all have these different I numbers, and I number 70 is given the name note. Meanwhile, user Jim here also has file 70 in their directory, but it's under the name memo. See how this works? Link makes a new directory entry that has the same I number as an already existing file. But that file name might be different. Removing one of these entries requires using the unlink system call. So even if we took out this entry here from Jim's directory, that file still exists because it's also under AST's directory. And if both of these are removed, then the file is deleted because there's no entries for that file anymore. So that's directory management. Well, actually there's more than that. We talked about mounting earlier. So mounting is where two file systems are merged into one, such as with the files on a USB drive. So, of course, we're going to have mount and unmount. A typical C statement for mounting is given here. So, the first parameter is going to be the name of the block special file for the drive. The second parameter is going to be... The second parameter specifies where in the tree are files to be mounted. The third parameter tells whether it's read-write or read-only. So we have this. So we have this directory here, and we want to mount something to here. After we mount it, the tree is going to look like this. So this is going to be the tree of our USB flash drive. We've mounted its contents to here, and now we can read those files. And again, this is different from Windows drive letters, by the way. The key takeaway with mounting that makes it different from a Windows system is that files from drives, you can mount them anywhere in the root directory. Okay. There are a few more system calls after this. So, change directory, that changes the current working directory. chmod changes the mode of a file, where the mode is used for protection. Kill is how users and user processes send signals. If a process is prepared to catch a particular signal, then a signal handler is run when it arrives. If not, then its arrival kills the process. Hey, catch! And then you die. Well, you as a process dies. And there's another one called there's another system called time. This is the number of seconds since January 1st, 1970, midnight. And this is a quantity that will overflow in 2038 if you're using signed 32-bit values, or 2106 if they're unsigned. So basically, it's a repeat of the Y2K problem, except we already have solutions for that, and a lot of them typically revolve around using 64-bit values, which, depending on how you're counting your time, whether it's seconds or microseconds, this would make it so that you wouldn't have to worry about an overflow for a few 100 billion years, or maybe a few 100 million years. It really depends on the specific implementations, but if we're going to be using Unix time for any longer, we ought to switch to a 64-bit system. And this is called the end of Unix time, by the way. So sometime in the year 2038, it's going to overflow, and then the system's going to think it's like and then the system's going to think it's the year 1900 or something like that, which is the basis of the Y2K problem anyway. The Windows Win32 API. So Windows has its own system calls, and they roughly correspond to their Unix equivalents. Well, not perfectly, because the Win32 API might have system calls that are unique to it. Unix might have system calls that are unique to it. But a lot of the important ones, such as fork, open, close, read, write, those have have equivalences in the Win32 API. The library calls and actual system calls in Windows are highly decoupled, and this set of procedures form what is called the Windows Win32 Application Programming Interface, or API. Programmers are expected to use these to get operating system services. So if a programmer on a Windows system wants to open a file, they don't call open. Rather, they would call create file. And if they want to close the file, you wouldn't call close. You would call close handle. It's worth emphasizing that Windows has a very large number of other system calls, and most of them don't correspond to anything in Unix. So what's up with this decoupling, by the way? It's this. This decoupling means that even if system calls are renamed, the names for API calls are preserved. So if behind the scenes, the names for system calls are different, at the programming level, nothing's gonna happen because, well, the names of these, well, basically the names of these functions that you call to get some operating system service, if they're the same no matter what the system calls are named, then you don't have to rewrite your programs. Okay, so that's 1.6, that's all about system calls. I hope I did a good job at trying to explain how system calls works, but just in case, if you have any questions, definitely let me know, okay? Okay, so now we're gonna look at operating system structure. Operating systems, there are 6 tried and true ways of structuring operating systems, but they are not the only ones. In fact, tried and true might be a little bit too restricted. I should say tried. And those are monolithic systems, layered systems, microkernels, client-server systems, virtual machines, and exokernels. So it's not an exhaustive list either. So this is just to give an idea of all the structures that have been tried in the past. And we're going to begin with the monolithic system. So here, the entire operating system runs as a giant program in kernel mode. The OS is written as a collection of procedures, linked together into a single large executable binary program. Each procedure is free to call any other procedure if doing so provides useful computation. Oh, and here's one nifty little trick about monolithic systems. If there is a bug in the whole program, and remember, the whole thing is one giant program. If there's a bug, it might crash the whole system. Oops. To make such a system requires compiling the individual procedures, then binding them into a single executable file using the system linker. Also, there's no information hiding. Every procedure is visible to every other procedure. But even then... Oh, by the way, have you ever written a program, but you didn't subdivide it into classes, you didn't subdivide it into functions? That's what it feels like. Though, hopefully I would hope that your programs are much more organized than that. Even if you had to write a monolithic system, at least, even if you had to write a monolithic program like this, it's still possible to have some level of organization. Even then, it's possible to have some structure in a monolithic system, usually showing itself up as the following. So we have a main program that invokes the requested service procedure. We have a set of system procedures that carry out the system calls, and then we have a set of utility procedures that help the system. A set of utility procedures that help the service procedures. So a monolithic system is one big program with all the system calls in it. The problem is if part of it crashes, the whole thing crashes. So if organization can still arise from a monolithic system, why not organize it like that in the first place? So that's a layered system. This is a generalization of the 3 layers of a monolithic system. In a layered system, the OS is built up in layers, and each successive layer is built upon the previous layers. You can't build a house without a good foundation. And you can't build a second floor without the first floor either. And you can't build a roof over that unless all the floors below it have been built already. Kind of like that. The first such layered system was the THC system. This was built by Edgar Dijkstra and his students. And yes, I mean that Edgar Dijkstra of the Dijkstra's pathfinding algorithm fame. So layers 1, 0, and 3, those manage the hardware. So that's layer 0 was the CPU, layer 1 was the memory, layer 3 is the I/O devices. Anything above layer 3 is where we would have our abstractions with I/O devices. So there is a further generalization to the layered approach, and this was present in the Multics system. This system consisted of a series of concentric rings, each inner ring more privileged than the last. So if the outer ring was all of our user programs, the innermost ring, which I guess is really just the core now, the innermost ring was the hardware itself. Above that we would have something like CPU scheduling, and then memory management, and then process management. Whereas THE's scheme was only a design aid, what Multics brought to the table is the fact that this entire structure was present at runtime and enforced by hardware. So with a layered approach, designers have a choice of where to draw the kernel to user boundary. What if we put as little as possible into the kernel? So why would we want to make a kernel as small as possible? We're putting we're putting as little as possible into the kernel. Why? To reduce the chances that there would be bugs. You can't have bugs if there's no code. I hope the camera caught that, right? Anyway, bug density per 1,000 lines of code. That's gonna vary based on module size, module age, but a ballpark estimate is something between 2 and 10 bugs per 1,000 lines of code. With a monolithic system of 5 million lines of code, we're looking at up to 50,000 bugs. Most of these aren't fatal, and many of them occur rarely, but that's a lot of bugs, 50,000 bugs. The idea is this: if we make our kernel as small as possible, we reduce the possibility of having bugs. So the basic idea behind a microkernel design is to achieve high reliability by splitting up the entire operating system into well-defined modules. And they're all small, well-defined modules. Only one module, the microkernel, is allowed to run in kernel mode. Everything else is in user mode. And unlike a monolithic system, where if there's a bug, it might bring down the whole system, if there's a bug in any of these supporting modules, it's only going to crash that one module. It's not going to take down the whole system. One such system is the Minix 3 microkernel. That only had about 12,000 lines of C code and about 1,400 lines of assembly code. If we go by these figures, we're looking at about, 15 bugs at most? So the C code manages and schedules processes, handles interprocess communication, and offers about 40 kernel calls to the rest of the operating system to do its work. So outside the kernel are 3 layers of processes, and they're all in user mode. So we have these 3 layers. They are user programs, servers, and drivers. So the drivers, that's the lowest level. The middle layer contains the servers, which do most of the operating system work, such as creating managing and destroying processes. And above that, those are the user programs, which obtain OS services by sending short messages to the service asking for the appropriate POSIX system calls. There's an interesting server called the reincarnation server. Its job is to check if all the other servers are working properly. If a faulty process is detected, the reincarnation server simply replaces it, and it does it automatically, no user intervention required. So a slight variation of the microkernel involves distinguishing between the two classes of processes: servers, which provide services, and clients, which use those services. So we end up with the client-server model. Often the lowest layer of this is a microkernel, but that's not required. So communication between clients and servers is often done by message passing. A client process constructs a message saying what it wants, and then it just sends it to the appropriate service. The service then does the work and then sends back the answer. All this might not be necessary if the computers... All this might not be necessary on a... Let me back up. If this is necessary on a computer and you're trying to have two processes on one computer trying to talk to one another, you can have ways to optimize that, but really the beauty in a client-server model is you can have a server be on a different computer from the client. Certain optimizations are possible if the clients and servers are on the same machine, but an obvious generalization is when you have these things running on different computers, all connected to a network. As far as the client is concerned, it's sending a message and eventually getting a response, regardless if it's going to a server on the same computer or to a remote computer. So because of this model can be used for both single machines and entire networks of machines. Excuse me. And now we get to virtual machines. So the initial release of OS 360, we briefly talked about that earlier in the book in the last video. The initial release of OS 360 were strictly batch systems, but many users wanted to work interactively at a terminal, so various groups inside and outside of IBM wrote time-sharing systems for it, and what was produced was TSS 360, delivered late and was too big and too slow to run. So a descendant of that was produced. That's called ZVM. Originally called CPCMS, VM370 was based on an astute observation. A time-sharing system provides multi-programming and an extended machine with a more convenient interface than bare hardware. And the essence of VM370 was to completely separate these two. So what's going on here? The heart of the system, the virtual machine monitor, runs on the bare hardware and does the multi-programming. This provides several virtual machines the next layer up. And these virtual machines aren't extended machines. They're copies of the bare hardware. And because each virtual machine is a copy of the bare hardware, it can run any other operating system that the bare hardware can. And it's not uncommon to run different operating systems on virtual machines. So there's a section in the book on virtual machines rediscovered. So IBM had a VM product available for 4 decades, and only recently did Oracle and Hewlett-Packard do something similar for their high-end and enterprise servers. Basically, VMs were a largely ignored topic until it became a hot topic because virtualization provided a means of testing servers on the same machine without crashing the entire server. also gives us the ability to run more than one operating system at once. So that way, if you have a program that only runs on a Unix system, you can run it on a Windows system. This is not an atypical use of a virtual machine, and there's a program called VirtualBox. This is a virtual machine where you can load it with a Unix operating system. You can load your program onto that, and then you can run it on a virtual machine that is itself on a Windows machine, or vice versa. To run a virtual machine on a computer, the CPU must also be virtualizable. So here's the problem. When an OS running on a virtual machine executes a privileged instruction, the hardware must tap to the virtual machine monitor so the instructions can be emulated in software. So on some CPUs, notably the Intel Pentium, these attempts were ignored, making it impossible to have virtual machines on such hardware. So basically, once upon a time, you were unable to ever run VirtualBox. You were unable to run anything like it. For that to work, you need to virtualize. The CPU must be virtualizable, and apparently, that's some of the hardware that we had at the time. No, can't do it. That said, there were interpreters for the Pentium, but this would incur a performance loss. So, even with these interpreters, the virtual machine would run up to 100 times slower than the base machine. Too slow to be useful. This would change around the 1900s and this would change around the 1990s and 2000s as several academic research projects, Disco at Stanford and Zen at Cambridge, would lead to several commercial products, VMware Workstation and Zen, among others. This research improved the performance of interpreters by translating blocks of code on the fly, storing them in a cache, and then reusing them if they were needed again. This led to what the text calls machine simulators. And this technique, called binary translation, was still not fast enough for commercial environments. The next step was to add a kernel to do some of the heavy lifting. In practice, all commercially available hypervisors use this hybrid approach and are called Type 2 hypervisors. If you wanted to run two operating systems at once, you would need something called a Type 1 hypervisor, or virtual machine monitor. That's what we were talking about earlier. What makes a Type 2 hypervisor different from Type 1 is that Type 2 makes use of a host operating system and its file system to create processes, store files, and so on. A Type 1 has no underlying support, and it's got to be able to do all of this itself. And then there's the Java virtual machine. This is another use for virtual machines, but it's different from what we've been talking about so far. So the Java programming language was made alongside the JVM so that Java programs can run on it. The Java compiler, as you might know, does not turn Java code into executable instructions. Rather, it turns it into something that the JVM can read and execute. The advantage of this is that a Java program can be written once, run anywhere, compared to if the compiler made an x86 program instead. If you wrote a program and you made it for Windows, you have to recompile the program for a different platform, say a Unix system. If you write something in Java, all you gotta do is transfer the executable jar file, and no matter what system you're on, as long as you're able to run the JVM on it, you can run the jar file. And there's another one called exokernels. So virtual machines clone hardware, but another approach is to partition the hardware instead. So one VM may get disk blocks 0 to 1023, another one gets 1024 to 1047, and so on. At the bottom layer, running in kernel mode, That's the exokernel. Its job is to allocate resources to virtual machines and make sure no machine tries to use another machine's resources. And each VM can run its own operating system. The advantage to this is that it saves a layer of mapping. In a typical VM, each VM thinks it has its own disk, so a VM must maintain a mapping between the virtual machine's disk addresses to the actual machine's addresses. And an exokernel doesn't need any of this. So those are the 6 kinds of operating systems as described in the book. Took a while for us to get through it. The recording's already at 56 minutes. So, we're almost done. There's only about 10 slides left. Actually, even less than that. So, I'm going to skip a few parts of the book and go briefly over how a large C project is compiled. So, this is just an overview of the process. We have a whole bunch of header and C files. They are compiled into an object file. The first pass of the C compiler is the C preprocessor, and then these things are compiled into .o object files, and then they're passed to a linker to combine them into a single executable. The last thing is about SI prefixes. Interestingly, 2 to the power of 10, that is 1024, and it's awfully close to 10 to the power of 3, that's 1000. Annoyingly, the industry standard seems to be fixed on defining a gigabyte as being 1024 megabytes and 1 megabyte as being 1024 kilobytes. That's technically incorrect. And that's because one system is going by powers of 2 to the 10, and another one is going by powers of 10 to the 3. So it means there's a discrepancy, between one system and another. And this is how you get nonsense like this, where you buy a 2 terabyte SSD, but it shows up as 1.8 terabytes. Where's my 0.2 terabytes? And that's because the drive is being marketed as being 2 to some power number of bytes, but the system is reading it as like 10 to some power of bytes. And it just causes a bit of confusion. And at worst, it makes it like you're being ripped off. Ideally, we should be using binary prefixes instead. So, kibi, mebi, gibi, tebi, pebi, exi, zebi, and yobi. Oh, interestingly enough, there are 2 new SI prefixes added. So now we have... Okay, once upon a time, we had to develop all these SI prefixes. So we have deca, hecto, kilo. That's where we got our kilobytes, because it's 1,000 bytes. Mega, giga, and then tera. And then we had to go with peta. And then we had to add peta, exa. And then after that, zeta and iota. And when I was first taking computer programming classes, the mnemonic that was taught to me to remember all of these prefixes was Yoda Pez Dispenser. Check it out. Yoda, P-E-Z. Yoda Pez Dispenser. But now we have Rona and Quetta. So now, I'm going to pass on this mnemonic to you. QR code, Yoda Pez Dispenser. There you go. QR code, Yoda Pez Dispenser. And then kilo, mega, giga, and tera are fairly easy to memorize. K is often used and as an abbreviation for 1,000. M for million, that's what mega is. T for trillion, that's what tera is. And the only mismatch is G for billion. Giga is 10 to the 9th, and that's 1 billion. That's the only mismatch you have to deal with. And that's how you memorize all of these prefixes. At least until you have to memorize the inverses. So we have deci, centi, milli, micro, nano, pico, femto, atto, zepto, yocto, ronto, and quecto. Also, there's no corresponding binary prefixes for Rona and Quetta, though they would presumably be called Roby and Quebi. So yeah, the textbook defines a megabyte as... The textbook, oddly enough, defines kilobytes, megabytes, and gigabytes as 2 to the 10th, 2 to the 20th, and 2 to the 30th. But then it uses transfer speeds of kbps, mbps, and gbps, kilobits, megabits, and gigabits per second, to mean 10 to the 3rd, 10 to the 6th, and 10 to the 9th. This is what I mean by it's confusing to have one system be overloaded for... I guess this is the industry standard right now, and it's a little bit confusing because you have a system meant for powers of 10 overloaded for powers of 2. This is just what the text goes by. This is the industry standard, so let's go with it, even though I really think we should ideally be using these to make it absolutely clear what we're talking about, and we don't have these weird ambiguities, and we don't have this weirdness happening where you buy a 2 terabyte SSD and where's my 2 terabytes? Where's my 0.2 terabytes? You know, yeah. So this is what the textbook uses, and if you ever wanted to memorize all of the SI prefixes, QR code, you go to Best Dispenser. There you go. Alright, so that's going to be the entirety of Chapter 1, except for a few extra slides that I had to omit. I would advise you read that in your own time, but starting with the next video, we're going to be looking at processes. So processes are the main thing that you learn in operating system. They are a program. Processes are a program in execution, and they're different from programs themselves because a program on a hard drive does nothing until it's loaded into memory. Then we're going to look into process scheduling, because if you have multiple processes on a computer, if you want to run multiple things on a computer, the computer needs some way to switch between the two. Or multiples. Okay. That's what we're going to be looking at in the next chapter. So, by the time you watch this video, it might be Monday already, so I'm going to do my best to upload this as soon as possible. It is around Sunday right now at the time I'm recording this, so yeah. Alright. With that, I'm not going to assign any homework just yet, but I might start assigning it in the following week or two. And we're going to begin looking at Chapter 1 assignments, and then I might add in stuff regarding Chapter 2. We'll see what happens, okay? With that, that's going to be it for this video, and if you have any questions, definitely feel free to email me. Stay safe out there. Don't breathe in too much. Don't breathe into smoke for too long. And see you next video. Thank you.